Yes, and we are back. We survived Thanksgiving, and we are back here doing the videos. Just Gannon and myself. Sorry you're not able to be in attendance. You're all watching videos now. Sorry about that. We rather have you here. So these last few classes we're just videoing. This is Monday. We're still wrapping up 14. Well, we're just doing problems today, really. We've covered all the principles for NMR. So homework 14 is due tonight. Quiz 9 is already posted on Learning Suite. It's a 4-page quiz, I think. You've got to solve some structures, and I think going through the stuff today will help you out with that. Um, so make sure you get that done. You'll have some time with the TAs. Remember, we still do recitation. We still do office hours on Zoom, so we're still live. Okay, at least in that regard. Chapter 15 is the last chapter. Yay! Usually there's a big roar of applause at this point, so I'll do it for you. There you go. Okay. The last chapter, radical chemistry. We'll do some radical halogenation, and we'll do some polymer formation. So it's an interesting chapter, a useful reaction with alkenes, and showing you how to do radical chemistry there. And then test 4 coming up, different format. It'll all be multiple choice, 40 multiple choice questions over chapters 12 through 15. The difficulty and content of the multiple choice is similar to the multiple choice you've seen already. Most of the problems are single concept problems, although some involve multiple concepts. And yes, we can still do mechanisms multiple choice, give you some different choices to choose from there. But yeah, it'll be 40 multiple choice problems. I think that comes out to what, 2.5 points per problem? Yeah. And then the final will be 70 multiple choice problems, and it'll be administered December 17th. These will be done as PDFs. You'll be looking at that under the exam tab on Learning Suite. It'll just be posted there for limited amount of time, I think around noon that day, and you have to do the problem, do all the problems on an answer sheet, and then scan that and upload that by midnight that night when those are due. So I'll say more about that when we get to it, but yeah, you'll see those. Sample tests, of course, for test 4, and there's a sample final already on there. It is cumulative, so it goes over all the chapters, 1 through 15. So that's the difficulty coming up there. So questions on that? All right, last time we left off with this complex splitting problem here with vinyl acetate. And the complexity here is that these 3 hydrogens on the alkene are all coupled to each other. They're all distinct sets, okay? These are not part of the same set here. This one is cis to the acetate, this one's trans to the acetate, and this one here has a coupling magnitude that's trans to B here and cis to C. So we have what, 4 sets, 4 non-equivalent sets in this problem. You see them all, they're right here. The easy one is, of course, the singlet here for the methyl group. But notice where it resonates, a little over 2, because it's alpha to the carbonyl this way. It's not right on an oxygen. That would make it higher shift, okay? And then the alkenes here, the patterns here, we have a doublet of doublets for D here. It's split with a large splitting right here, which is like 16, and then a smaller coupling right here. So a doublet of doublets. That's not a quartet. A quartet would have the outer lines worth 1 and the inner lines worth 3. Okay, it's a 4-line pattern, but we call that a doublet of doublets. That's for D. Then B right here has that larger coupling. You still see that. And then the small coupling for the geminal coupling here to C. And then HC has the smaller cis coupling that we see here, okay, in HD. And then that small geminal coupling right there. I like the book goes through a little bit of analysis here for the patterns. You see the doublet of doublet, and that's how it's split out. The larger coupling here is that trans coupling, which is what, 14? Yeah. Can be up to 20, which is nice for those trans relationships. And then we've got the smaller cis coupling here. For HD, go back and look at that shift-wise Let's see. Yeah, it's way up here around 7. That's because it's alpha to that oxygen. That's what ranks it up there. Normal alkenes are around 5, but because it's alpha to that oxygen, it's way up there at 7. Anyway, there's the full analysis of it, doublets of doublets. Okay, so the complexity can go up there. Now, this combines with a problem we saw in chapter 13, IR, and mass spec. We looked at this formula, mass spec 88, IR 1710, carbonyl here, and we could arrive at this molecular formula, C4H8O2. Now remember, we started out with multiples of carbon. Carbon is worth what, 12 atomic mass units? So you can kind of go up there and then figure out, you know, how many hydrogens you need. You have to have a reasonable amount of hydrogens here. You can analyze how many units of unsaturation you have. The maximum would be what? For C4, it would be H10. And we have, what, 2 less? So 1 unit of unsaturation. So we have 1 double bond or 1 ring. So here are some structures. These are all C4H8O2, but now we're combining with what? The proton NMR. And this is higher resolution, 500 megahertz. So these coupling patterns show up very nice. And this ester right here, notice, is distinct from this ester and this ester here. And this ketone, ether. We proposed all these structures in chapter 13, but now you can see the proton NMR. These are all very distinct, aren't they? So here we have our quartet triplet. That's diagnostic for what? An ethyl fragment. And notice that quartet for these 2 hydrogens, alpha to the oxygen, is shifted what? Far downfield. This is highly deshielded at 4. That's because it's right there. Then notice we have that same ethyl fragment here, but here our methylene thing's alpha to the carbonyl. So where is it? It's 2.4 now. It shifted much higher, what, upfield. It's more shielded. And there's our singlet floating around. It's up here at 0.7. That's because it's alpha to the oxygen right here. Whereas here our singlet was what? Alpha to the carbonyl. This is further upfield. So these are distinct. Make sure you can look at those proton spectrum for each one and analyze why those shifts are where they are. But the same pattern. You see the quartet triplet, singlet, but they kind of move around. And then for this one, we see a propyl fragment. And the diagnostic one is this one, this methylene in the middle, because it's coupled here as a triplet and over here as a quartet, right? But that's 5 equivalent neighbors. Remember, we said if the magnitude of the coupling constants are similar, you can just consider it as a multiplet of those equivalent neighbors. So 5 neighbors, n plus 1 then means it's a 6-line pattern. There it is right there, the hextet. It's in the right spot too. It's not alpha to this oxygen, it's beta to it. So it's a little bit further downfield. This one that's further down here is the methylene, what, right next door, alpha to the oxygen. So yeah, that's the triplet right here, okay, because of the 2 neighbors right there. And then the aldehydic hydrogen's way up here at 8. Why is it so far deshielded, so far upfield? Well, it's right next to this partially positive carbon, okay? That's highly electron deficient, which leaves this proton nuclei highly exposed to the magnetic field. It requires higher RF frequency to flip it out of resonance with the magnetic field. So you can remind yourself of those shift patterns. But remember, for test 4 and the final, we'll give you a data sheet where you'll see the shift ranges of everything. Okay, it's similar to that to the one on the chapter outline. And then this one here is distinct, I think, because they're all singlets. They're all isolated, no neighbors. But the shift position should be diagnostic there. By the way, this is how we do the line listing of the NMR, proton NMR data. Delta, what the shift is, how many hydrogens, and then what the multiplicity is, okay? And you'll use that for quiz 9. We remind you of that on quiz 9 to report your structures that way with the line list. All right, going back to the original thing we looked at, right? Ethanol here. Here's our friend, our triplet quartet, alpha to the oxygen, yeah, way up there. HC is the hydroxyl. We need to talk a little bit about that. No coupling there, because next door is a methylene. How come it's not showing up as a triplet? Right, it's hydrogen bonded. So there's a dynamic effect here. It's not always localized on this oxygen, so it will not show any couplings to anything. And plus, it's variable where the shift will be. It depends on the concentration and how much hydrogen bonding going on. This can be variable. This can be found anywhere from 2 up to 5 or so. Usually it's more broad. This is a high field instrument where it's quite sharp. But usually it's a broader signal for an alcohol. Same thing for amines, NHs, also hydrogen bonding. Another trick you can do here is you can treat the material with deuterium labeled water, D2O. Shake it with D2O, it'll exchange the hydrogen for deuterium, and then deuterium will not show up in the proton NMR. So this signal will actually disappear if you treat it first with D2O. That's another diagnostic test for seeing if you have an alcohol or an NH group. Okay. Here's a couple other things to look at. Proton NMR for cyclohexane. But all 12 of the hydrogens are the same. They all resonate at the same place. So no splitting. That's just one equivalent set. They don't split each other, right? And there it is. That's all you see. What, at 1.4 or so? One singlet. You can't tell much there from the proton NMR. You'd have to use what? Mass spec to nail that structure down. So proton NMR is not the end all here. You can't use it in isolation. But if you put a chloride on there, look how things change, right? This is just cyclohexane. Remember, he sits in its complexity here because of the chair conformations. You have all these non-equivalent sets now with the axial equatorial positions. I think there's 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7 non-equivalent sets. If you consider this single chair with this equatorial, right? And that's flipping with the other one as well. And then one furthest downfield, if it is exchanging rapidly, which it is in this case, this hydrogen has how many neighbors? 1, 2, 3, 4. So yeah, it's a 5-line pattern here. It's a quintet. If they're all equally coupled there for that hydrogen right here. Okay, that's the one downfield now. And these ones here are kind of close to the chloride right here, and then all these are kind of piled on top of each other in very complex coupling. You can't really tell much from there. Here's cyclohexanol, similar issue with a lot of non-equivalent sets now. And this is at a low field instrument. I think this, yeah, 90 megahertz. So this is one of the old instruments, okay? Back when I was an undergraduate, this is all we had. And you can see things are very blobby there. It's hard to tell what's going on. But if you go up to 400 megahertz, these things sharpen up, and look at the resolution's a lot better. That's because at 90 megahertz, each ppm, 0 to 1 or 1 to 2, that's only 90 hertz resolution power. But if you're 400 megahertz, each ppm is 400 hertz, okay? The coupling constants stay the same. So you get much better resolution. So here you can actually see the axial equatorial positions, and there I assign them. You can look at them. Here's the one at 2.9, this one alpha to the oxygen, yeah, 3.6 right there. And you can see 1.9, 1.7. You can do a complete analysis here and see they're all different. You have to do a couple more experiments, correlation spectroscopy, to nail all these down. But they're all distinct. They all show up at different spots. You can see that at higher resolution for that. Another thing to say about benzene. We did show you some benzene proton spectra, and they're kind of messy. So look at ethyl benzene. And we're just looking at the aromatic region here. And look at this. These 5 hydrogens on the benzene, because the 6 position's taken up by the ethyl right here. So this would integrate for 5. But you can't really tell, you know, what are the ones adjacent to the ethyl, or the next one over, the one here furthest away. We'll learn those as the ortho, meta, and para positions in 352. But they have the very similar shifts. They pile up on top of each other. And that introduces another concept. It's called second order coupling or magnetic non-equivalence. And when the shifts of highly coupled things get very close to each other, then the complexity of the line patterns goes way up, and you see a lot of lines that you can't interpret. It's not scalar coupling. It's not n+1 the rule that we've learned for normal signals that are well separated. And so for here, we just say, oh, that's just 5 hydrogens multiplet. You're okay to just call that a big bunched up multiplet. But if you have an electron withdrawing group, like an aldehyde, and you can draw some resonance structures here with a partial positive charge out here at these ortho positions, that will begin to shift these hydrogens next door to the aldehyde further downfield. So right here we see a nice doublet for these 2 hydrogens, okay, that have those guys next door, 1 neighbor each. So that's a little bit better. And then these 3 here even separate out a little better. So you can begin to see, and plus integration, you'd see 2 to 1 to 2. You'd be able to interpret that. Anything next door to an electron withdrawing group, you can draw a resonance structure with a plus charge here and here. We'll shift those signals further downfield toward 8. And then this is more electron rich. The lone pairs can donate in and make these positions next door more electron rich. And so these are shifted further upfield. They're a little bit, below 7 right there for those 2. So if you have a donor or a withdrawing group, then they begin to separate a little bit out better. You have to be on a high field instrument to see that. But if it's just an alkyl group or something that's not strongly polarizing the electrons in the benzene, they'll all just bunch up together. You just call it a multiplet. And that's okay. So here's spectrum of a typical aromatic one, this phenyl ethyl alcohol. And here's our pattern for the, let's look at the ones upfield first. Big doublet integrating for 3 right there, okay, because 1 neighbor. Yeah, around 1. And then here's our OH, our alcohol that could wash out with D2O. And there's a quartet, which is coupled to the methyl right there, and it's far downfield because it's alpha to the oxygen and it's benzylic. It's next door to the benzene. That's in the de-shielding cone, remember, of the benzene ring current we talked about, that diamagnetic anisotropy effect, which anything on the periphery here is shifted further downfield. And then the ones right on the benzene, here's the 5 here. But look at how messy they are. It's a real haystack here, especially at the lower frequency. But, you know, it's kind of a thing that sticks up here. So we just say, you know, 7.2 to 7.3, 5 hydrogens multiplet. That'd be fine. But the rest is sharp, right? Quartet at 4.9, singlet at 2, and then singlet at 1 point, or a doublet at 1.5, and then what the patterns are for that. Okay, here's a nice one to show aromatic-wise, a nitro toluene. So we've got a methyl here and a nitro group. The nitro group's strongly electron withdrawing. These 2 ortho hydrogens here, they're shifted far downfield. They each have 1 neighbor. They're part of the same set, so we only see a doublet split by that one and then split by that one, which is the same, equivalent, right? You have the mirror plane relationship there, so you only need to look at the one side to get the pattern. You see 2 doublets way up here. The one at 8 is the one ortho to the nitro. You can draw a resonance structure for that. And then the 2 here are next to the methyl. And that's a pretty clean pattern, right? 2 doublets way up here, integrating what? 2 to 2 to 3 for the methyl, which has no neighbors, so no splitting there. But it's in that shielding or de-shielding part on the periphery of the benzene. So it's a little bit further downfield compared to a normal alkyl, which would be up here around 1. Anyway, that's a good one to look at. I like to show this. This is a marine natural product called Palawamine, discovered about 10 years ago at a sea sponge in the Pacific Ocean. Scuba divers, so natural product chemists scour the world looking for new natural product compounds that have interesting activity. Mainly they're looking for compounds that have important activity against different diseases. This one has activity against certain forms of cancer. It's a very complex natural product, has a lot of nitrogens in it. Have to apply the nitrogen rule here. The structure was misassigned a couple times until they finally got a good high-resolution X-ray structure. At first, they were relying upon NMR and 2D NMR to figure out the structure. Some of the diagnostic signals are shown here. I'm not going to go through the whole thing, but don't have time for that, and it's beyond the scope of this class, but I like to show some more complex things here. The ones in red here, you can kind of assign what they might be. This HB right here has one neighbor, so this should be what? A doublet. And it should be, you know, further upfield, we'd say. This HD is alpha to this nitrogen, so that'd be further downfield. And look, how many neighbors does this have? Well, this neighbor right here is not the same. A lot of stereocenters here. So this methylene, these two hydrogens right here are what? Diastereotopic. They'll show up at different spots. So HD will be coupled geminally to this one and then vicinally to this one. So it'll show up as a doublet of doublets. How about this HA here? Alpha to that chloride. That'll be further downfield, okay? Above 3. And how many neighbors is that? Well, that's one here. It's not shown, but that hydrogen's right there on that methine carbon. So it should be a doublet also. And then this one on this nitrogen, okay, it'll be the same as this one here. And how many neighbors? 2. So these will show up as a triplet probably. Now, I'll just show you part of the thing. Well, okay, so there's the whole thing, the whole proton spectra for Palawamine. It's difficult to see, but down here around 3, this is diagnostic, the ones we just talked about. The other ones, there's a lot of aromatic ones and some alkyl ones further upfield. And then here's kind of a blow up of that region around 3 we were just talking about. And here's that one, yeah, 1.4 for HD. So that's off this chart here. But then let's see, these ones at 3.5, where are they? 3.5 or 3. Oh, there we have 3.3 and 3.27. So this one's showing up and this one here. They're right there. And that's a nice doublet, this high doublet right here. So you can see these, right? And what about this one right here? This one here is a doublet of doublets, and you see it right there. And then this one right here, 3.52, there it is right there. Yeah, it's a doublet of doublets. That's what the DD stands for. So that's how natural product chemists and NMR spectroscopists assign the full structure. And they have to assign each atom, okay, to determine it, to nail it down. Combined with C13 NMR and then 2D NMR that we'll show you in a little bit. Here's a diagnostic thing, law enforcement to figure out cannabinol, THC, which bind to the cannabinol receptor in the brain. This one binds very tightly to it. This is out of marijuana, right? And here's the proton NMR spectra for it. A lot of alkyl stuff, and a little bit down here in the aromatic region. You see you got oxygens on the benzene here. So these hydrogens here and here are shifted upfield, okay, because it's electron rich there. But then a lot of alkyl stuff, kind of hard to see there. These allylic hydrogens right here and here you can see. And this little one right here on the alkene, you can see where that is, right? Right there, okay, 5.3 or whatever. This is spice, or erroneously sometimes called synthetic marijuana. It's a very different compound. It's an aromatic ketone with an indole here. It binds more tightly to the cannabinol receptor in the brain. It's more potent actually than THC from marijuana. But law enforcement has a hard time with this because the victims show the similar symptoms with high doses of marijuana, but it's different. It has heart toxicity issues. And there are people who have died all around the world by taking too much of this synthetic marijuana stuff. You can see the NMR is very different. They finally isolated enough of this out of some victims to determine that this was a very different compound than cannabinol. They were using mass spec at first, and it was kind of confusing. 314 peak for the mass spec, whereas this is 341. The 2 digits here are just switched. And at first they were confused about that. And they didn't have enough to get a good proton NMR, but they finally did and nailed it down to see that this so-called spice or synthetic marijuana is very different from that. And you can see it just based on the appearance and the positions. A lot of aromatic stuff here, right? A lot of aromatic hydrogens, very different from this one where there's only a couple in the aromatic range. All right, let's look at some problems here. So this one, so here's the problem, right? Here's the proton NMR spectrum. unknown compound, molecular formula. Oh, we're giving it to you, darn. And sometimes we'll give you the molecular formula or we'll give you the mass spec. Okay, so sometimes you got to figure that out. But that's where you need to start. 8 hydrogens, right? And here are the hydrogens you need to account for. Oh, and you're told it's got a carbonyl stretch, 1740 or whatever. Here's a line list of the signals, okay? And then you see the actual spectrum. Here is also the integration, which is sometimes not exact, right? So we have to figure this out. Triplet here, and if you think that's a methyl group, 5, divide these others by 5 here. So you get 3 to 2 to 2. You can kind of see that 3, 2, 3. Yeah. And does that add up to 8? Yeah, 3, 3, and then 2. Yeah, so there they are. So singlet here at 3.5, and then quartet, and then triplet there. So what's the structure? So let's go to the board here, and I've got the same data written up there, and let's try to analyze this, right? So here's the data you're given. Sometimes you are just given the mass spec, 88, right? But you could figure out this formula here, right? And then here's the line listing of the data here. You see this triplet quartet here, and this one's far up field, right? So maybe a methyl, right? And then how many neighbors does this have? Is this a triplet? It must have 2 neighbors, okay? So for that guy, with 2 neighbors, that piece right there, we can already kind of see what's there. And by the way, you can see triplet quartet. What's that? That's your ethyl fragment. We'll review the common fragments you need to look for in the proton NMR. And so this one here is probably these 2, right? With 3 neighbors here, quartet, but no other neighbors over here. So there's something stopping the coupling right there. And then this one, 3.7, so that's probably next door to an oxygen here with no neighbors. So this one here, you know, has something on it like that. So believe it or not, just from this fragment analysis, I think we can propose a structure, right? But we have to have another oxygen here, and 1740 is a carbonyl, right? What's this 2900 or 3000? That's just alkyl CH stretch, okay? It's not an alcohol. That would be up at 3500. Okay, so let's piece it together. A carbonyl, this, and where are we going to put the ethyl, and where are we going to put the methyl? That's the choice here. We have an ethyl and a methyl. Where are they going to go? Here or here? Okay, so what do you think? Let's put the ethyl over here because it's at 2.3. So I think this would be the logical choice. Okay. Do you agree? Or is it this? Or do we put the ethyl here next to the oxygen and the methyl here next to the carbonyl? Which one is it? Reinspect the data and see. Check your shift table, whatever. This one right here, right, is alpha to the carbonyl this way. Yeah, that's around 2.5, 2.4, whatever. And that's consistent with what we see here, okay? If it was this one here, our quartet would be up around 3.5, okay? Well, that's too high for the data, right? Our singlet is okay up here at 3.5, 3.7, whatever. That's because it's alpha to the oxygen right here, yeah. So, yeah, I think this one is the one that's consistent with the table and what we know about the shifts there. But you get a feel for this, right? The mass spec and the IR helps us kind of focus in on a couple things, and then the common patterns that we can see in there. Let's review some of these common patterns, okay? So we've got a methyl singlet, okay? Well, we have another singlet kind of thing here, which could be a tert-butyl, okay? But the integration, this one would be 3 hydrogens. This one would be, what, 9 hydrogens for a singlet, okay? See singlets all over the place. What else could we see for a singlet? Well, an OH that could be variable or broader, okay? That would also be a singlet there. Or anything else that's isolated and has no neighbors. So anything where n equals 0. And then let's see, what other type of pattern have we seen? How about ethyl? Okay, and there we see our old friend quartet, a triplet, and what? Integration 2 to 3, okay? And that's really typical of ethyls. If you have two identical ethyls, though, this could be 4 to 6. Okay, you have to be careful of symmetry there, but that pattern is very common. What about isopropyl? We've seen a couple of these also. What's the pattern here? Well, it has a big doublet and then a little multiplet. And a lot of times the isopropyl is coupled to something else here, so at least it will show up as what? A heptet, okay? And the integration will be what? 6 to 1, okay? So if you see that type of pattern, big doublet, and this will always be up around 1, okay? And same with this, any of these terminal alkyls around 1. Heptet, depending on what it's next to, it could be next to an oxygen, which would make it further down. But anyway, that's a common fragment. What about tert-butyl? Well, there we've got that. Oh, we just did it. Okay, big singlet. Okay. Oh, what was the other one? Propyl. Okay. Propyl, what do we see here? We see a triplet, a multiplet. Okay, sometimes we don't see it. Or maybe a quintet. Or no, what would it be? Yeah, hextet. Yeah, okay, because it has 5. Yep. What about this one? Depending on what it's coupled to here, this one might be a a triplet also. Okay. So yeah, triplet with 2 neighbors here, right? And this one multiplet because it's coupled over here and here. And then this one, depending on how many it's coupled to, yeah. So an N-propyl, you see, it's going to be a lot different than an isopropyl, right? Where you got the big doublet, little heptet, okay? So those things I think we can keep in mind and keep straight. Let's do a couple problems on the board here, just with the line list data. How about this one here? We've got 4.0, multiplet 1H. We've got 2.4, singlet 1H. And then we've got 1.2 doublet 6H. Okay, well, you already can kind of see here 6H, 1H, doublet, multiplet. Already thinking about a couple things here. But let's look at a couple other things here. Mass spec, 60 for the mass to charge, and IR, 3500 broad. Okay. So what are we thinking about here? 60. How many carbons can we really have there? Not too many. You can go through the analysis here and come up with this pretty quick. But I'll include the oxygen here. Well, this broad 3500 really screams alcohol, okay? So yeah, you got an alcohol here, and then 8 here, you can kind of go back and see, yeah, 6, 7, 8. Okay, that's good. So some back and forth there between the data. So what do we come up with for this? Well, 6H here, doublet, what does that look like? It's this, right? And that's really about all we can get. 3 carbons here, right? And here's 1, 2, 6, 7. So where's the 8th? Oh, we've got to add an oxygen here, right? So we can really narrow it down pretty quick to this, isopropyl alcohol. And that's consistent with all the data. You can go back through and work that problem if you'd like. But again, we're not showing you the actual spectrum. We're just showing you the line listing of the data. And some of the problems are that way. All right, let's do another one here. A little bit bigger molecule, a little more complicated, I think. Let's see. Here we've got 1.2 singlet worth 9 hydrogens. Then we got 1.3 triplet, and it's worth 3 hydrogens. And then we've got a 4.1 quartet worth 2 hydrogens. Okay, and we'll give you the molecular formula C7 H14 O2. Okay, what is the structure? Oh, we'll give you IR also. There you go. So how many non-equivalent sets do we have? 1, 2, 3. And does that add up? Yeah, 5, 9, yeah, 14. O2, 7. And this is kind of hard to tell. C13 NMR might be helpful for that, but you can already see, what's going to be on there and what functional groups you might have. So you can tell right away, you've got what, a carbonyl. Okay. And now I think you just piece together the fragments. 9 hydrogen singlet. What is that pattern-wise? Yeah, it's a terbutyl. Okay. It's pretty much all it could be. No neighbors. You'd have to have something on the quat carbon, right? These all 9 are equivalent there. No splitting. And then what's this? Triplet quartet. Well, that's our old friend ethyl, right? Here's our quartet right here. Okay, 2 hydrogens. And here's our triplet right here, further upfield at 1.2. This is the delta value. Sorry, I didn't put the units in there. So what can we get up to? And how many carbons do we have so far? 1, 2, 3, 4, 5, 6. We need to get up to 7, and that's probably our carbonyl, right? And then 2 oxygens. So what do we need here? Well, yeah, we've probably got an ester again, right? And then it's what fragments do we put on what side of the ester? That's often the issue here. So let's see, where's our shift of our quartet? 4.1. So that should be pretty clear. Our ethyl group needs to be on this side of the oxygen. So where's our terbutyl? It's right here, okay? So yeah, that is the structure for that. You may have come to this point and said, okay, our terbutyl could look like that on that side of the oxygen, but this here would be what, at 2.5, not at 4, 3.5 or 4, okay? So this is too low. This needs to be the structure right here, not this one, okay? All right, questions on that one. Let's look at a couple other things here. Yeah, that's the one we just did there. Yeah, and we came up with the right structure there, I think. And there's what the spectrum looks like. Okay. C13. We need to talk a little bit about C13. That's very similar to proton NMR, but here we're looking at the C13 nuclei. What's the relative abundance of C13 in natural samples? The atomic mass on the periodic table is 12.011 AMU. That's the weighted average. So how many C13 nuclei that weigh 13 atomic mass units are there? Right, it's 1.1%. So it's very insensitive. So you see right away a very noisy baseline because you have to take many transients, you have to run many experiments and add them together to get the signals to grow out of the bottom. And here's a molecule with 2 carbons. So we're looking at the carbons here now. It's tuned to a different frequency. We always decouple all the hydrogens. They can couple there. We never see carbon-carbon coupling because it's very rare to have 2 C13 carbons together, so we don't need to worry about that. Then we decouple the hydrogens. We can't integrate things here. They have different response values, so it's not like proton NMR that way, and they show up as single lines. So it's just the position within the 0 to 200 ppm range. It's a much wider spectral window here, much wider frequency units, and we'll show you that. So here we've got the methyl group way up here at 20, and then the carbonyl down here at 180, and that's typical for carbonyl compounds. Acids, of course, down there, and then methyl, an alkyl way up there. Here's the shift values. There's basically 2 domains. Anything below 100 is alkyl carbons, sp3. The higher range in the 100 unit is alpha to electronegative groups. So anything with an alcohol or an amine or a halide will be shifted further downfield to an alkyl. Alkynes a little bit kind of on the border there, but anything alkene and aromatic is up here above 100 toward 200. Carbonyls are way up there, close to 200. They're very diagnostic for that. So just to show you a few here, and again, we're looking at C13 NMR, not proton NMR now, okay? So here are the 3 carbons for propanol. You see them there. This one here has the oxygen on it, so it's further downfield. And then B is that middle one, and then C is the further one away from it there. And then we've got an ester here. You see the carbonyl for the ester way up here, around 170. And then the other 2 here, alpha to the oxygen, yeah. And then this alcohol, how many there? 1, 2, 3, 4. And again, it's sets of non-equivalent carbons. With symmetry, you can have similar carbons. And that's this ketone right here with 2 ethyl groups on the ketone. These, the 2 methylenes are identical, okay? The same symmetry, so they're right there. And then the 2 methyls are the same right there. So there's only 3 non-equivalent sets here, the carbonyl, the alpha to the carbonyl, and then the beta to the carbonyl, the methyls. And so you just see the 3. But you see the very noisy baseline there, and that's because the relative rarity of C13, you have to run a lot of samples. Okay, here we go. This is MRI, right? And a lot of you who were here in class last week said they had had an MRI image taken of their body. And here's the big donut. Here's the permanent magnet. And the person lays down on there. And the frequencies shift. There's some banging and clanging that goes on there. The more modern instruments are a lot quieter now. In the old days, they were very claustrophobic. In fact, I think this is an older instrument here. The hole is kind of small. The newer ones are bigger, less claustrophobia going on there. But it takes a 2-dimensional scan through a slice of the image there. The computer's able to focus on it, and it's mainly looking at the density of proton and phosphorus 31 nuclei. And it can image the soft tissue very good, okay, because cells, the nuclei especially, have a lot of phosphorus in them due to the DNA. And then the other tissues, mainly with water, higher water content, that's the proton NMR. So it takes a scan there, a 2-dimensional scan, and then by tomography, it builds up a 3-dimensional image of what the body looks like inside. So it's non-invasive, okay? It's just RF frequencies. There's no ionizing radiation. It is still a nuclear event, the spin of the nuclei changing with the radio frequency that's applied, but there's a lot of computer imaging that goes on here. And so here's an image of someone's spine, I think, and you can see a ruptured disc right there. The material is leaking out of the disc into the spinal column and giving them problems. I don't know if they're paralyzed or whatever, just have a lot of pain. You see this disc isn't ruptured. These are okay here. These are normal here. But here's the ruptured disc right there for A. A lot of terms here for the anatomy there. It's even worse than OChem, memorizing stuff, right? To memorize all those little terms there. But MRI allows you to image those kind of things. And it's a correlation spectroscopy. So how do you get to this 2-dimensional image or the 3-dimensional image? Well, you start to correlate the 1-dimensional spectra. And so just to show you a little about this is correlation spectroscopy, or COSY it's called. Proton to proton correlating, and it can tell you which protons are coupled to each other. So here's a aromatic amide. There's 2 benzene rings here. A lot of proton, so this is a proton NMR down here at 7. And it's hard to say which is coupled to which, right? It's difficult to do the full assignment. This broad one here, NH, that's hydrogen bonding. So that's broader right there. So that's A. You can kind of determine that one. But let's say this green O right here, what's it coupled to? Well, it's coupled to the green M right here. And you do this correlation spectroscopy. I'm not going to describe how the experiment's done. It's a spin system evolution process, and the computer has to do this. On the diagonal here are the regular signals coming up from the 2 proton spectra, which are on the Y and the x-axis here. But then the off diagonal peaks are correlation peaks. So we see here this green O here correlating the red line over here to what? The green M right here. So you can see what's coupled to what. That lets you make that assignment there. And then you can do green P, and you can also do the black ones here. That's the blue lines there. But this is a relatively simple compound, but let's say you do the full correlation and do the complete peak assignment there, which would be ambiguous if we just relied on the one-dimensional proton NMR. Het core is another correlation spectroscopy. Here's two different nuclei, right? C13, which is right here, the X, and the Y-axis is the proton. And all the peaks in the field here are correlated. So what this means on this carbon right here at 121 has this proton at 760. Okay, so you can begin to see this. Here's the one for the carbonyl way up here. So we're just looking at this window right here. These are the ones that have hydrogens on them. And you can begin to make the assignments there to see where different protons are on different carbons. That lets you do a full correlation. Now for MRI, you have to do that for proton and phosphorus, and then the density. And by tomography, you build up the image there. So it's not a line spectra thing. It's more of a density thing, but it's a similar idea, correlating where those peaks are. Let's do this. So here we have some problems. We got some time here. Let's see how many of these we can do. These are line lists of the problems, and you're given enough data here to propose a structure that's consistent with that. So let's do as many as we can here and see how this goes. So this is, again, combined with IR. Here we're giving you the formula, okay? So by mass spec, we could figure that out. So here we have some that are similar, and we'll have some symmetry issues. A couple of these are really hard, I think. I always have to go through these a little bit carefully and figure these out, but let's go to the board then and do these, Gannon. So this first one here, structure A there, I'll just summarize the data again here. So we have delta 1.8 singlet. It's worth 6 hydrogens. And then we have 3.8 singlet, 2 hydrogens. Okay. And the formula is C4H8Br2. Okay. So yeah, there's our 8 hydrogens. Okay, so yeah, you should always make sure your number of hydrogens you're thinking about is consistent with how many are in there. But how are we going to do this? 6 hydrogens are the same that are singlets there. Well, that's what methyls, CH3s that don't have any neighbors on them. Okay, so they're insulated that way. And same thing with this. This would be a CH2, but with no neighbors there. So how can we do this? Well, we have to have some bromides on the carbons, right? And we're only down to 4, so we could just kind of start to draw some structures here. Can we put the bromides on here to give this pattern that's correct, right? Well, here we have the 2 methyls here, and what if we put the bromides there? Okay, well, right away, can you see a problem with this structure? This would be coupled with that, and it wouldn't be a singlet, okay? So this was a no-go from the beginning, even though we're starting to think about these 2 methyls being the same, right? And this one here, and this is further down, you know, it's downfield, 3.8, whatever. Let's think about this. What if we do a branched thing here? And that's nice because 2 methyls could be what? The same if we put a bromide there, okay? Yeah, okay, so that kind of solves this problem here, this being a singlet, right? And these are the same, right, 1.8. And then that leaves this here. We don't have another methyl, and we need another bromide. That's nice. Let's just put the other bromide there, okay? So what do we get? Yeah, 2 right there, 3.8. Yeah, and that turns out to be the correct structure, okay? So, you know, some of these, you just start to draw a carbon fragment and think about how you could build that up. I think thinking about branching here solves that problem of having no neighbors there. All right, let's look at the next one. Which is this data here, 2.4 quintet, 2H, okay, and then 3.5, this is the delta value, triplet, 4H. And this is C3H6, Br2. And you see our 6 here for the 6 hydrogens, okay? But this is trickier, right? Quintet and triplet? If this is a triplet, that means what, it has 2 neighbors, but you don't see a quartet, you see a quintet. And this is tricky too. 4 hydrogens? What's that? That's not a methyl. It's not an ethyl or an isopropyl. How do we get 4 hydrogens? Well, 2 equivalent CH2s maybe, okay? That have a total of what? 2 neighbors to give them a triplet maybe? And you only got 3 carbons anyway. So I kind of jump ahead here and just say, okay, let's just put it on here and let's see where we can put the bromides, right? Let's put a bromide here and here. Well, this is a problem right away because you only have 2 non-equivalent sets here. And this structure has 1, 2, 3 non-equivalent sets. So that's a no-go. Well, what about this one? How about if we put the 2 bromides in the middle? Well, then we just have 2 methyls, 2 CH3s, right? So that's a no-go too. Well, how about the only other one really is this. So here, I'm trying to point out, experiment with it and think about it. You may not have thought about this structure to begin with, but this will turn out to be the correct one. So let's go back and look at the data. So let's see. Methylene, methylene, yeah, with 2 neighbors, and they're equivalent there to the symmetry, right? And so, yeah, this will be a triplet, 3.5, okay? And all 4 of these will be equivalent, okay? And yeah, triplet for 4H. That's good. And what about these 2 here? How many neighbors? 1, 2, 3, 4. Yeah, quintet. There's your quintet. I think this is kind of a tricky one. Even though it's a relatively simple formula, this one forces you to begin to experiment with structures. And that's what I told you before. You're solving little puzzles here, okay? You're looking at the data and trying to figure out a structure that's consistent with all the data. And this is the only one. These are off by quite a bit, okay? Let's see. Let's do a couple more. Let me do this one, D. I think it's further down there. Okay, 0.8. It's a triplet, and it's got 6H. And then we've got 1.0 singlet, 3H. And then we've got 1.5 quartet, 4H. And then we've got 1.6 singlet, 1H. In this one, if you treat with D2O, it goes away, okay? So that's what, an alcohol, okay? Now I'll give you a little bit here on this C6H14O, and the IR has a 3500. So what can you tell right away? And you've got that, right? So alcohol, okay? So you're already thinking about that. And 14,6, that should make some sense. That's the maximum amount, so you don't have any rings or double bonds, so no carbonyl, okay? So you have the maximum amount, so no rings. So this one's a little tricky, and this one you really have to start to think about this. So a triplet, 6H, okay? So that's probably 2, what? With what? 2 neighbors, right? So, and it's got 2 of them there, okay? So it's a terminal methyl group with a methylene with 2 neighbors making a triplet. And you've got 2 of them. Okay, so it already says something about symmetry, I think, okay? And then you have this one, 3H singlet around 1. Yeah, that's just a methyl with no neighbors, okay? So that fragment there. Now here's our quartet with 4 hydrogens. Well, that's probably this guy right here, okay? Again, the symmetry idea. So what do you probably have? You probably have 2 ethyl groups. Okay, you see that? And then we have to have an alcohol. There it is right there at 1.6. And let's add up everything here real quick, right? We've got, 14 hydrogens. So we're consistent with that. So can we draw some sort of a structure? Well, this OH here has to be on something, right? But notice there's nothing here shift-wise that has a hydrogen downfield. So this carbon right here, what? Probably doesn't have any hydrogens on it. So let's see, can we put the fragments on there? Well, we need 2 ethyls, okay, there they are, and a methyl. And we've got a quat carbon. Is that the number of carbons? 1, 2, 3, 4, 5, 6. Yeah. Hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, we've got the hydrogen. And is that the right structure? Okay, well, you might, think, well, there could have been some other ways to do this maybe. Here's 2 ethyls, and how about the methyl on the oxygen? Well, that's not an alcohol now, okay? So we can't do that. And plus, this would be a more complex thing, and we'd have this around 3.5. So this is a no-go, okay? It's this quaternary alcohol here with 2 identical ethyls on it. You can draw that a couple different ways. So let's see, how about like that? Looks kind of funny, doesn't it? But there's our CH3 with no neighbors. This CH3 has 2 neighbors, right? So that's triplet, right? And this has 3 neighbors, so that's your quartet. And that's identical to this one, so it's doubled. You have 4 and then 6. And then this one is the 3H. Anyway, I think that's a harder problem due to the symmetry, okay? Forces you to think about it, to propose some fragments and then link them up together, okay? That's how we'll get through some of those. Let's just show a couple of these others here to wrap up again, and you can go through the rest of those there. There's the answers there. Here's another one with symmetry. This diisopropyl ether. I think that was D there, the data in D. Yeah, and there you see the 6 and the 4 again. Yeah, okay. There's an aldehyde one there. Let's go back and see that one. Oh, that's the one down here at 9, 9.8. Yeah, look at that triplet. And that's this guy. It has 2 neighbors right here, right? That's on an aldehyde. That's 9. Okay. Here's a couple other proposals here. You can see an ethyl fragment there, and there's some isolated ones. And I think we did that one before too. Yeah. In fact, we proposed this in chapter 13, actually. We just did one like that. And then these here, you're given the formula nitrogen, right? And you can see it's a primary amine because you got 2 H's right here. Yeah. It's a singlet. Yeah. And a couple H's there. Yeah, you're given the integrations here. And these inset spectra are nice too because it blows up the signal, so you can see the splitting a little better there. But yeah, 2 triplets, so that's 2 methylenes next door. That's that one there. And then the NHs, and then the aromatic, the 5 hydrogens there that are a mess up here. So just say 5 hydrogens multiplet. 5 hydrogens multiplet, that's fine for that one. And then what's this? Oh, this is a reaction one. You take this alcohol, treat it with tosic acid, which is like sulfuric acid, and you do a dehydration reaction. So you're going to form 2 alkenes. And these alkenes, one is the Zaitsev, more substitute alkene product. One is a less substitute, the minor product. And I think you get to this. Here's your major one. You can go through the mechanism, protonate the alcohol, form the carbocation, do the elimination there, get tri-substitute alkene. And that's, I think, this one right here. Yeah, because there's 1 hydrogen up here that's a triplet. This 1 hydrogen is coupled to these 2 right here. So that's in the 5 region. And you can see it's a little triplet. Yeah, the others, the methyls are singlets, I think. These methyls aren't coupled to anything. But these are different. This is the cis-methyl. This is the trans-methyl. So these will be different. So this is a non-equivalent set. You have 1, 2, 3, 4, 5 sets there. There they all are. 1, 2, 3, 4, 5 sets. And then here's your minor one, the alkene forming out here, which is di-substituted. And what's this one? Oh, here you're given a ketone, which has a lower resonance there. And I need to talk about this one a little bit. Let's go to the board and talk about that one. This carbonyl here is at 1680. Why is this carbonyl at 1680? 80 in the IR? That's a good question, isn't it? You can see the propyl fragment here. We've talked about that. You can see the aromatic thing. And these two hydrogens right here, these are at 8 ppm. Why are they so high? And why is this carbonyl so low in the IR? Well, let's do resonance, right? Double-headed arrow. And what do we get? We get an important resonance contributor where what? The bond order here, the carbonyl is not fully 2 now. It's lowered. And what? We have a plus charge here, okay? This is a significant resonance contributor to this molecule, okay? We say this is an electron withdrawing group. We'll talk about that a lot more in 352. But if you draw the resonance structure here, putting the negative charge up on the electronegative oxygen, that's true, that lowers the density here electronically that this hydrogen sees. This is more exposed now to the large magnetic field. So this is shifted further downfield. It's toward 8, okay? Partial plus charge. And plus the bond order here went from 2, okay, with a double bond, and now it's lower here, okay? This doesn't mean this is the true structure of this ketone. This is an important resonance contributor to the true structure, which has the electron density on the more electronegative oxygen, which lowers the bond order here, and you see that in the IR, okay, 1680. Anyway, I think there's a problem in the book too that has, this reaction problem. Here's a line list of some data for an epoxide. I think you can go through and assign that. There's the structure of the starting material. You had to come up with a starting material here. So we can link NMR problems to reactions. And if you treat that epoxide with HCl, you'll protonate the epoxide, and then chloride will backside attack in the major pathway and open up right there because that's the benzylic position, okay? So you can see the data for this. And these two hydrogens right here and here are way downfield. This is a singlet, and this is a doublet, this methyl here. So I think that's good. And then this is that last problem. This is similar to the one we just did for the ketone there. If you draw the resonance structure here, you have partial positive charge here, which shifts this alkene, which normally alkenes are 5 to 6, right? This alkene is at 7. Why is it so far downfield? Well, it's the resonance contributor has a partial positive charge at that beta position, okay? H8, A is okay, that's right there. And you see a doublet there for A, and that's that 14 hertz coupling right there. And then you see a smaller coupling here, B to C. So this shows up as a doublet of triplets, and it's right here. There's 2 big triplets, which are kind of close to each other. But that's for B there. So to do the full analysis here, you'd say HB, this one at the beta position is right here. That's that one. When you do the full assignment, that one's there. What about these upfield ones here? Well, alpha to the ketones around 2.5, and allylic ones, HC, you can't tell those apart. Those are right next to each other. And then these 2 here are right here, these 2. And they're a complex pattern too because they're a triplet of triplets, okay, which are on top of each other right there. So that's how NMR really looks like. Even with relatively simple compounds, you have to do the analysis there. But I think that's well enough here. We did enough there. We'll review, of course, NMR again before test 4 and for the final, but NMR we can use it a couple different ways. So work as many problems as you can. Propose a structure. Get to the point where you're trying to propose a structure. Don't just try to interpret one little part of the data. Jump ahead and propose a structure. That's always the key. Very good. And we'll see you on Wednesday. Okay.